Time, it's something we experience every second of our lives, yet it's far more mysterious than it seems. We assume time flows at the same pace everywhere, but what if I told you that time actually moves differently depending on where you are in the universe? If you were standing on Jupiter, time would tick by slower for you than for someone on Earth. If you were near a black hole, time could stretch to the point where years might pass in what feels like minutes. But why does this happen? What causes time to warp and bend across different planets and celestial bodies? To understand why time moves differently, we first need to talk about Einstein's theory of relativity. You've probably heard of it. Einstein discovered that time isn't absolute. Instead, time is affected by two major factors: gravity and speed. This means that depending on how fast you're moving and how strong the gravity is where you are, time can either speed up or slow down. This phenomenon is known as time dilation. Let's start with gravity. According to general relativity, the stronger the gravitational pull, the slower time moves. This is because gravity isn't just a force. It actually bends the fabric of space and time itself. Picture space-time as a giant, flexible sheet. When a massive object like a planet or a star sits on that sheet, it creates a dip or a curvature. The deeper the dip, the stronger the gravity, and the stronger the effect on time. This means that on planets with higher gravity than Earth, like Jupiter or Saturn, time moves slightly slower compared to here. The difference is tiny, fractions of a second per year, but it's real. If you lived on Jupiter your entire life, you'd age just a little bit less than someone on Earth. It's a minuscule effect, but it becomes much more dramatic near incredibly dense objects like black holes. But gravity isn't the only thing that affects time. Speed plays a role too. According to special relativity, the faster you move, the slower time passes for you compared to someone who's stationary. This is why astronauts on the International Space Station, moving at about 28,000 kilometers per hour, actually experience time slightly slower than people on Earth. If an astronaut lived in space for 50 years, they would return to Earth a tiny fraction of a second younger than their twin who stayed behind. Now, let's combine these two effects, gravity and speed, and apply them to different planets. A planet like Mercury, which orbits the Sun much faster than Earth, would experience a slightly different flow of time due to its speed. Meanwhile, a planet like Jupiter, with its immense gravity, would slow down time more than Earth does. But the real extremes of time dilation happen in places far beyond our solar system, where the effects of gravity and speed push time to its limits. Now, imagine standing on the surface of a neutron star, one of the densest objects in the universe. These stars are only about 10 to 20 kilometers in diameter, but can be more massive than our Sun. Their gravitational pull is so extreme that time moves significantly slower compared to Earth. If you spent just a few hours on a neutron star and then returned to Earth, you might find that years had passed for everyone else, while only minutes or hours had passed for you. This is time dilation in action, and the closer you are to a massive gravitational source, the more extreme the effect. But nothing warps time more dramatically than a black hole. Near the event horizon, the point of no return, gravity is so strong that time slows to an almost complete stop relative to an outside observer. If you were to hover just outside the event horizon of a black hole for a short while and then return to Earth, you might find that centuries or even millennia had passed here. This is exactly what happens in movies like Interstellar, where astronauts experience only a few hours on a planet near a black hole while decades pass elsewhere. This isn't just science fiction, it's real physics. So, what does this mean for time on different planets in our own solar system? While the differences are much smaller compared to extreme cosmic objects, every planet experiences time slightly differently due to its unique gravity and motion. For example, Mercury. As the closest planet to the Sun, Mercury moves at incredible speeds, completing an orbit in just 88 Earth days. Because of its high velocity, time moves just a tiny fraction slower there compared to Earth. However, Mercury's gravity isn't strong enough to have a noticeable gravitational time dilation effect. Venus, with a gravity slightly lower than Earth's but a very slow rotation, time on Venus isn't significantly different from Earth's Mars. With just 38% of Earth's gravity, time on Mars moves slightly faster than it does on Earth. But the effect is so small that an entire lifetime on Mars would only result in about 0.1 seconds of extra time passing compared to Earth. Jupiter, with its massive gravity, time moves slightly slower than on Earth, though the effect is minuscule over a human lifespan. Saturn, Uranus, and Neptune. These gas giants also have stronger gravity than Earth, meaning time moves just a tiny bit slower on their surfaces. While these time differences are tiny compared to the effects near black holes, they are real. If humans eventually colonize other planets, we might experience time in subtly different ways. Astronauts who live on Mars for extended periods will technically age a little faster than those on Earth. If we ever establish colonies on massive exoplanets, time could slow down for those settlers compared to people back on Earth. But what happens if we travel even faster, closer to the speed of light? According to special relativity, if a spacecraft were to travel at 90% of the speed of light, time would pass more than twice as slowly for those on board compared to people on Earth. If we could reach speeds of 99.99%, the speed of light, time would slow down to the point where a journey that feels like a few years for the crew might mean thousands or even millions of years pass outside their ship. This means that future space travelers could theoretically visit distant stars and return to Earth to find entire civilizations have risen and fallen in their absence. This idea, time dilation through high-speed travel, is one of the biggest challenges for interstellar travel. If humanity ever develops the technology to travel near the speed of light, our perception of time will be fundamentally different from those who remain on Earth. Future astronauts might experience a journey that feels like months or years, only to return to find Earth has aged by centuries. But here's where things get even weirder. What if time itself isn't constant across the universe? Some scientists propose that the expansion of the universe affects time itself, meaning that distant galaxies may experience time differently than we do. If that's the case, time might not just move differently on different planets, but on a cosmic scale, entire regions of the universe could be experiencing time at different rates. If time flows differently across various planets, stars, and galaxies, what does that mean for the nature of time itself? Is time something absolute, or is it entirely relative to where you are in the universe? The answer, according to Einstein's relativity, is that time is not a universal constant. It's a flexible, ever-changing dimension that bends under the influence of gravity and motion. This leads to some mind-bending questions. If different planets experience time at slightly different rates, could there be a place in the universe where time stops entirely? Theoretically, yes, right at the event horizon of a black hole. If you were to watch an object falling into a black hole from a safe distance, you'd see it slow down more and more, appearing to freeze in place as it approached the event horizon. However, from the perspective of the object itself, time would seem to flow normally. This paradox highlights the strange and counterintuitive nature of time dilation. But let's bring it back to something more familiar, our own planet. Even here on Earth, time doesn't move the same for everyone. Someone living at sea level experiences time just a tiny bit slower than someone living at the top of a mountain. This is because the closer you are to the center of the Earth, the stronger the gravitational pull and the slower time moves. In fact, GPS satellites orbiting Earth experience both gravitational time dilation and velocity time dilation. They move fast enough that time runs slightly slower for them, but they are also farther from Earth's gravity, where time runs slightly faster. Engineers have to account for this discrepancy by adjusting the clocks on these satellites, or else GPS systems would gradually drift out of sync with reality. This means that even within our daily lives, time is subtly shifting based on our position and movement. It's an effect so small we never notice it, but it's measurable and crucial for modern technology to function. So, what does all of this mean for the future of space exploration? If humans establish colonies on Mars, Jupiter's moons, or even planets beyond our solar system, the people living there will experience time slightly differently from those on Earth. While the differences will be tiny in most cases, for deep space, travelers moving near the speed of light or settling near extreme gravitational sources, time could become a true barrier separating civilizations. Someone living on a high-gravity planet might age years behind their friends and family back on Earth. A future astronaut traveling at near-light speeds might return to find Earth unrecognizable, having moved thousands of years into the future. This isn't just a fun thought experiment. It's a real challenge for future space missions. If we ever send humans on interstellar journeys, they may not just be exploring the stars, they'll be traveling through time itself. In the end, time is far more complex than our everyday experience suggests. It bends, stretches, and warps depending on where you are and how fast you're moving. Every planet, every moon, and every star exists in its own unique flow of time, subtly different from all the others. And as we venture further into space, we won't just be exploring new worlds. We'll be stepping into new timelines where the ticking of a clock is never quite the same.